All right, here we have a discussion of the first chapter from the McMurray text. If you find this helpful, I hope you make good use of the time. There are a lot of things we have to measure in chemistry. We use the system of units that are commonly thought of as metric units, but which are actually known as SI units, a French name we don't have to pronounce. These are common to our uses in chemistry. The abbreviations are in the right column, and there's some that will be used far more frequently than others, particularly mass length, temperature. We'll talk about amounts of substances in moles, and then seconds. The last two on this list will not be so commonly used. Others will be derived from these units. You'll need to become familiar. There are times when the measurements that we're describing are very large or very small, and we don't often like writing all the zeros. And so our best way to go at this is using scientific notation. The scientific notation will also be simplified by using prefixes. The prefixes shown in this chart from your text are the common ones. I would add to that you should probably like to be familiar with micro and nano. You'll hear about them from time to time, maybe some of the others, but not so often. And so the equivalence between the prefix and the factor power of 10 is what we need to get familiar with. So for example, with a centimeter, 1 centimeter is 0.01 meters, which is the same thing as 10 to the minus 2 meters, which is what it says right there. Or a kilogram, or a kilogram, let's do kilogram. A kilogram is going to be 10 to the third gram. So 1 kg equals, 10 to the third gram. So wherever you can write kilo, you can substitute 10 to the third. And it helps us to understand these relationships. The other feature with these is that folks sometimes are not happy with the exponents that are in negative values. And so if you wanted to say that a centimeter is 10 to the minus 2 meters, well, that's not, there's nothing wrong with that. But some of you would prefer to think about it in another sense, where you realize that if you multiply both sides by 100, you'll get an equivalent relationship, and that means that you have 1 meter equals 100 centimeters. So that works equally well. You just need to be comfortable with how these can be used to get from one unit to the next. Again, being familiar with scientific notation is very helpful here. So let's think about these in terms of examples. So if you're thinking about the length of the Colorado River in the Grand Canyon, it's a lot of meters. 446,000, and we're going to try to put this in scientific notation. The way we do this takes some practice. So what you have to recall is that this is 10 to the 1, this is 10 to the 2, and this is 10 to the 3. If you had 10 to the 1 is just 10, 10 to the 2, that's 10 squared, or 100. I'm going to put that as 10 times 10. 10 to the third, oh, the tool is being a little persnickety, sorry folks. 10 to the third is 1,000. In other words, 10 cubed is 10 times 10 times 10. It's nice to refresh our thoughts on these things, because sometimes we haven't used them for a little while and we get a little bit forgetful. 10 to the fourth is 10,000, or 10 times 10 times 10 times another 10. Well, we're up to 446,000, so we haven't got far enough yet. In other words, another way of thinking about this is the number of zeros after the 10 in your exponent. The number of zeros after the 1 is the same as the number in the exponent. So 10 to the fourth has 1, 2, 3, 4, or 4 places after the initial digit. This value here has 1, 2, 3, 4, 5 places after the initial digit. So that would be 10 to the fifth, which I didn't finish writing. 10 to the fifth is going to be 100,000, but this is more than 100,000. It's 4 times 4.46 times 10 to the fifth. And so the answer that would be correct here is E. I hope that makes sense to you. All right, let's try another one. Let's do negative exponents. Oh, those are more exciting, more challenging. Keep us on our toes. The diameter of a nickel atom has got to be pretty small if we're thinking in terms of atoms of a metal called nickel. The scientific notation expressed in meters is going to be what? Well, first of all, you have to know what PM means. It's not afternoon in this case. So 270 picometers is going to be expressed in meters only if we remember what the relationship is. So P in this context is pico, and it means 10 to the minus 12. Whoops, 12, there we go. And you just have to know these, get familiar. But in the case of doing homework, by all means, you can look them up. And so wherever we can put pico, or P in the abbreviation, you can put 10 to the minus 12. So you have 270 times 10 to the minus 12. Well, that's not proper notation because you want a number between 1 and 10 in that spot. So you need to restate the 270 also in powers of 10. So that's 2.7. Let's try fixing that. Thank you. 2.7 times 0. Keep the 0 because it was there. Times 10 to the what? Well, remember that however many places are after the initial digit tells you the power of 10 here. So that's going to be 10 squared. And then we're keeping the negative exponent of this portion on the other end of the calculation, or the calculation, whatever here. And so now we have to decide what to do with the 2. We're finished to simplify this. What you do with exponents when they are multiplied. When you're multiplying exponents on powers of 10, the number in front is unchanged, and the exponents, the value of the exponents will be added. So 2 minus 12, or 2 plus negative 12, is minus 10, which would be this answer here. All right, I hope you tried that before I got to the right answer. In meters, they didn't put the M here, but we should have 2. Be careful to include your units. It's really wise to keep you going straight. All right, so now how about measuring mass? And mass is kind of a funny topic because we sometimes think about mass and weight differently. And on planet Earth, we don't really distinguish one from the other. Mass is simply the amount of matter in the object. And when it boils right down to it, chemistry is the study of matter. So we think about mass when we're trying to describe what's happening in chemical processes. Matter is anything that has a physical presence. You have to be able to touch or taste or smell. Something that has mass is going to be matter. The difference between mass and weight is a little bit subtle. It depends on the object's location. In other words, if you were on the moon or Mars, it would have a different weight. But the gravity exertion that we like to describe is typically for planet Earth, so we will stick to the description as mass. That's what we'll commonly use. All right, so what do we use to measure mass? Of course, balances. Some of them are more high-tech than others. The top loading balance, such as shown in the right, are quite simple to use, and you'll have a chance to do things like that when you get to the lab. Let's think about what the system, or the common metric unit is. The SI unit is the meter. And the meter has got a funny history. It was defined originally in 1790 as a relative to the distance between the equator and the North Pole. How they did that in 1790 is quite mind-bending to those of us who wouldn't have done it. And later they redefined it as a distance between 2 lines on a bar of platinum iridium alloy, PT and iridium. Apparently they like that for its stability. It was stored near Paris long time back, and then nearly 100 years later they redefined it as the distance traveled by light through a vacuum in a certain amount of time. Wow! Let's not try to memorize those. So if you want to have comedy about metric units, we can talk about temperature too. Well, Vinny, now that I've turned another year older, I'm only talking in terms of Celsius. We're not talking about temperature, I presume. I didn't turn 86, Winnie. I turned 30. In other words, these two silly old ladies are talking about the fact that 86 Fahrenheit is the same as 30 Celsius. So she would like to describe her temperature or her age in Celsius. And so what else do we know about temperature? Well, sometimes it's cold outside. We have that in North Dakota in our quote-unquote spring semester. The different units for temperature comes on the different scales, and we need to be aware of the relationships between the different scales. And particularly relative to specific important things. The freezing and boiling point of water are thing that determines life on Earth as being possible is water, and so we like to relate to these. Celsius and Kelvin are the most common used in our chemistry course. You will hear references to Fahrenheit, so you kind of need to have a perspective where they are. 0, okay, so a mild winter day might be 0 Celsius, and 100 degrees more than that is the boiling temperature of water. And the Celsius scale, again, has the same distance between boiling and the freezing points of water, 100. So the size of the degree is the same. This increment change is the same in Celsius and Kelvin. They just differ by the starting points. One is 0, one is 273 if you're talking about beginning at the freezing point. Of course, in Fahrenheit, if you grew up in the US of A, you're probably familiar with Fahrenheit. And the freezing point of water is 32, which is 180 degrees less than the boiling point. And so that difference in temperature between the freezing and boiling point tells you that the change for each degree is a little smaller than it is in Celsius. It's 5/9. 5/9 is, in other words, the ratio between those two differences of 180 Fahrenheit degrees between boiling and freezing and 100 degrees Celsius between boiling and freezing in Celsius. So those are good things to know. 32 and 212, okay, those are the Fahrenheit numbers, but you want to be familiar with the boiling and freezing points of water in Celsius and Kelvin. Now, of course, some of you have lived in the North Country long enough to know that sometimes it's way too cold outside, and if you hear the reports in Celsius, there is this funny thing at 40 below. It doesn't matter because in both scales, and it's not shown on this one, the temperature of minus 40 Celsius is exactly the same, calculated out, you'll find out, as minus 40 Fahrenheit. So we're just hoping we don't have to see one of those too often. Now, there are these nice equations, relationships for calculating changes between Celsius and Fahrenheit. Fine, there they are, use them when you need them. But the one we're going to most commonly think about is Celsius and Kelvin. And all you do is add 273 to a Celsius value to come up with Kelvin. All right, now let's see if we can do this. I want to give you a tip here. This is a multiple choice question the way it's set up, and the intent is to give you some clues that sometimes help you. And we're going to figure out, and I told you we don't like to do them very often, but sometimes we will, how to get from Fahrenheit to Kelvin. You can guesstimate if you can put yourself in the right perspective. Now, some of these things are going to be easier to see than others. If you can see that 212 is the same as 373 Kelvin, are we below or above 373 Kelvin? Well, 173 is going to be somewhere in here. Yeah, I don't know, make a guess. It's somewhere in there. So it's going to be below the 373. So answers C and D have no bearing whatsoever on our choices. That helps. And now in order to come up with a Kelvin temperature, to get it correct, we'll have to go to the equation to find Celsius first, and then we can get from there to Kelvin. All right, so degrees Celsius equals what? Think back for 1 minute and see if you remember what the equation is, or flip back to the previous slide. Celsius is going to be described as 5/9 of the Fahrenheit temperature minus 32. So let's do that. 5/9 of the Fahrenheit temperature, which is this number here, 173.1, minus, that's supposed to be Fahrenheit, there you go, minus 32. And so we got to get out your piece of paper, your calculator. You can do this on paper if you try. All right, so put your calculating mind to work, and the answer of this becomes 5/9 times, the answer to that part is 141.1. Challenge yourself to do it without a calculator. And then you have to multiply 5/9 times that, and I've worked it out to make sure we're not getting lost. And I get the answer is 78 point, let's see, double check me here, 4 is the degrees Celsius. Well, clearly that's not the answer here because we're looking for Kelvin. And in order to get Kelvin, it's going to be Celsius temperature plus 273. And so if we add 273 to that, what do you get? I just did the math, and only if you put the 0.15 on here will you get an answer that shows up above. And my answer here, oh brother, tool is being funny, sorry about that, gang. It's going to be 51.45, and we're going to round that up and call it answer B. All right, hope that makes some sense to you. Let me fix that little error. Okay, hopefully that makes some sense to you. If in doubt, you should always ask more questions. All right, then there's derived units that have to do with things that are requiring more than one unit and more parts to them. Area, volume, density, and speed, for example. And these are examples of those that are in metric units or derived from the metric units. And there are some of these we will spend more time on than others. You need to think about them to get them right. And volume. Those of us who grew up in the US of A are not always comfortable with liters and milliliters, but it's time that we should be. You know what a 2-liter bottle of pop looks like, I suspect, or something similar. And we're going to think in terms of meters and milliliters and how do those relate to each other. So a cubic meter is one cube that has a meter on each side, and that's a lot of little parts. It's going to be 1,000 cubic decimeters. A cubic decimeter is a cube that has 1 decimeter on each side, but a decimeter is equal to 1/10 of a meter. 1/10 of a meter. Deci means 10 to the minus 1 or 0.1. And so if it's 1/10 of a meter, there's 10 of them in every meter. A decimeter on each side turns out to also be the same thing as a centimeter on each side. And so, wait a minute, 10 centimeters. So 1 decimeter equals 10 centimeters. So a decimeter cubed is going to be a cube that has 10 centimeters on each side. That is a liter. And it also equals 1,000 cubic centimeters. And that's one of those relationships that are very commonly used in our chemistry examples. So a cubic centimeter, which is this example over here, is also known as a milliliter. Those all make sense if they add them up correctly, but those are just good things to know. Let's do an example or so here. Other things that you need to know about volume is we'll use various devices in the laboratory. A graduated cylinder is convenient for measuring volumes of liquid as long as we don't have to be particularly detailed in the amounts. A volumetric flask is very accurate because it allows us to get exactly, in this example would be 50.0 looks like, and maybe 2 zeros, but that number of milliliters. It's harder to do that in a graduated cylinder. And a syringe is used for more detailed amounts as well. This one looks like it's a 5 cc syringe, which is the same thing as 5 milliliters. Cc means cubic centimeter. Sometimes in the lab you'll use this thing called a burette, and that would be used to measure liquids as they drip out the bottom into an experimental flask. Derived units include measuring density. Density has to do with mass divided by volume. Perhaps most of you have seen this somewhere. We need to refresh our thought. Mass divided by volume is called density. And so it's going to be grams per milliliter or grams per cubic centimeter, depending upon where you see it reported. Milliliters and cubic centimeters are the same, so it's effectively the same thing. Densities of various substances are provided in this table, none of which you should have to worry about except for the one that's most commonly encountered is water. And water is going to be a density of 1 gram per cubic centimeter at its most dense temperature is approximately 4 degrees Celsius, 3.98, 4 Celsius. And so the relationship between density and mass and volume is something we will use in our calculations on occasion. Another one we will talk about is energy. Measuring energy is going to be that which is needed to do heat or supply heat or do work. It's going to have 2 different kinds of units that we'll see. One of them is the SI unit called the joule. Capital J is a French derived thing and it has a definition that's shown here. And the second one is the one that's commonly seen in nutrition contexts, and that is a calorie. The calorie has to do with the way that water is heated. It takes 1 calorie for every gram of water to be heated 1 degree Celsius. We'll come back to that later. But in nutritional calories, that's called a capital C or capital calorie or something. It's kind of a funny thing because it's very subtle, because a small c and a capital C look the same. But a capital C calorie is 1,000 calories, and 1,000 calories is what we would also call a kilocalorie. And so that's the one you'll see on food labels, is this type of calorie. And it is going to be related to joules by that value there. 1 large C calorie is 4.184 kilojoules, because 1 small c calorie is going to be 4.184 joules. Numbers to remember when you need them. Let's not fret over them for the time being. All right. There's not too much left of this chapter. Let me pause for 1 moment. This is a good place to pause and resume a recording at with a different topic. I hope these are helpful to you. Please let me know if there's clarifications you require.